Compactness. Compactness in topological space or compact space, or sometimes called compact in topological space, and the another thing is compact in metric space. But the compact in topological space is more generalized than compact in metric space. There are some little features are different. Um, Compactness actually it arises before reveal. Uh, it arises in a sum of Euclidean pairs, and they are have some closed and bounded set. But it formalization mostly come from the sequential compact. I think it comes from the Bolzano, and you may know that as you got this mm, Bolzano-Weierstrass theorems. Uh, but now we will start the study from the beginning. Uh, Many of the most important theorem in a uh, classical analysis are proved for closed and bounded intervals. As we know, for real interval, this is a real interval R, and this is a closed interval AB. This is a compact set we know in real analysis. A continuous function on a closed and bounded interval assumes its maximum. The basis for the proof of such theorems is almost without exception. You may know that in Hahn-Borel theorem, What's a Hahn-Borel theorem? A cover of a closed bounded subset of the real line by open set has a finite subcover. That's all. This theorem has a extraordinary profound consequence, and for reaching applications in analysis, it is not surprising them. This property of closed and bounded set of a real line, thus expressed, has been made the subject of a definition in topology. The definition of compactness through at the same time it is to be noted, and boundness cannot be satisfactorily defined in an arbitrary topological space. That the notations of compact topological space and abstraction of certain important properties of the set real numbers, and in which incidentally strength versions of the Lindelof property. But we are mainly concerned about the basic properties of compact topological space, and later on you will learn about check compactification, check stone compactification. But here we mostly discuss on this topics of uh, basic ideas and basic properties. This is main, and the most applications of these things is that it is used in higher cases when it's needs. That's all. It has some sufficient conditions. Some sufficient condition it's have, but I will first start the what I will do it may be I discuss in real line it is one dimensional, but in two dimensional the closed disks are the compact, like this. Closed disks are compact. Actually, we first define what is a compact, then we will again come to this place. Actually, you may know that various definitions of compactness has been used, and we know that compact, this is a set or space. If we can define by some finite cover, this is called cover, Then this space, it has 1, 2, 3, 4, 5, 6, 6 cover. So from union of 6 covers, the finite cover, the digit 6 is the finite. If infinite, it is not compact, but it has 6 covers. Cover. If it has no finite cover, does not imply a compactness. This is the definitions. This is described in very lucid language. Not equal. We will first define for the case of Euclidean space. What is the definitions of compact in an Euclidean space? Sorry, it has something wrong. Not a Euclidean space. Euclidean space is there because Euclidean has not formed any space. Euclidean space compact when if and only if it is closed and bounded. Then an Euclidean space is compact. To define definitions of compactness. The standard definitions: a topological space X, non-empty set, is called compact if and only if every open cover of the set X has a finite subcover. This is the definitions. Can I say open cover as open set? Yes, you can. Then this will be subcover will be open subsets. You may know that when we will cover converted into set, you may know that, and that time we will say that the collections of open sets has a collections of finite open subset. That's all. It has no such big deal. It is for the case of some of the Euclidean spaces. Now I will define about open cover. Open cover. Let Open cover, what we will define? We must define C is the collections, but open cover, C, because we will U is uh, defined as open set in our discussion. Mostly I used C is an open cover. Okay, if each of its member is an open set. We cannot understand. The statement will be clear. Let C be a cover of a topological space X. We can write like this: U of alpha if I will not be wrong, see the collections will be union of U of alpha and this, and alpha belongs to the index set. It must be a finite, belongs to index set, and this is a open set. Open set. Open set. It will be mostly clear if our discussion. I will just change some things on it. Write it once a moment. You, if you will think X is a point at topological places. X is a point. So what we will see, X is a point in a set topological space and X is a set. A topology is defined on the set X. This is the matter. So for each X belongs to U of X, this is a open sets. Open sets. Okay. This is a topological space. Set. A topology is defined. This is topological space. Topological space. X. This is a point in the set X. This is the open set. Open set. What will happen? C collection of covers. This is formation C. If I will draw on here, it will be the bad in the pictures. A C is like this. Like this, C1, C2, C3, C4, C5, C6, C7, C8, and this is C9. But it may be infinite. I'm just trying to make it easy, that's all. This is the picture. This is the collections. C is the collections of covers. When C is the collections of covers, C is equal to union of U of X. This X belongs to the topological space X. Yes. This is the collections. This is the collections of the covers, and each cover is C1, C2, C3, Cn. If the number of the collections, now X is equal to is not exactly the correct things. Why? Because the cover cannot have such the boundary that is the strictly maintained. In general case, union of Ci, I is equal to, I belongs to indexed finite, infinite. Compact space. Yes. If the covers, if the number of covers are not finite, then it has open cover, but not exactly compactness. But we are not going to discuss that it may have semi-compact, paracompact, and most refinement. It may have. We are not going to the discussions, but we are discussing in a preliminary stage. This is not compact space, but it is compact space only the cover has finite number of covers implies compactness. That's all. So it is uh, so it's make it easily discuss, and sometime it may have the discussions that two topological pairs. One is the cover is this, and one contain this. So we can write down this subset of this. Okay, that's all. So we get these conversations. Union of alpha belongs to a finite. We think is that this is finite. Uh, U of alpha. Sorry, not U of alpha. Uh, yeah, no, this is correct. The line is not wrong. This is correct. This is finite. But I want to talk about X subset of union of alpha belong to index it C of alpha. This implies this is a collections of open covers finite. This implies X subset of union as alpha belongs to index set U of alpha. Uh, it is most accurate. We'll write down this. Uh, This is not finite. In this case, it is not necessarily finite. This is the things. Sometimes locally finite. A compactness x. A cover of x is said to be locally finite if every points of x has a neighborhood that intersect only finitely many sets in the cover. C is equal to U of alpha is locally finite for any x belongs to x. What will happen? There exists a neighborhood of x define n of x. What will happen? Alpha belongs to a set A such that U alpha intersection n of x not is equal to phi. This alpha is finite. This is the definitions of locally finite. This result may comes later. And refinement. Refinement, it is used on the check cohomology, but we are not discussing check cohomology right now. Refinement is refinement. We will discuss about it, but it is mainly it role in cohomology. It is uh, another part of algebraic geometry, but its topics used in algebraic topology. It has a applications in algebraic geometry, but its topics mainly shown in uh, algebraic topology. Um Actually, why cohomology is related on these topics. Actually, cohomology theory, uh, just a minute, it is related. For this, I will touch it. Cohomology theory, uh, based on the intersections properties of affine covers of a topological space. So we can realize the uh, difference between this. But we will talk about refinement. Refinement, in simply, what we will talk about it, but I will just formal sentence. A refinement of a cover C of a topological space X is a new cover D of X such that every set in D is contained in some set in C. What if I will think that D is equal to V beta, beta belongs to B, is the refinement of C cover U alpha, alpha belongs to A, if for all beta belongs to B, there exists alpha belongs to A such that V of beta subset of U of alpha. Okay, it is not still not clear. Uh, if you think a map F from B to A, you can see satisfying find V beta subset of U F of beta for all beta belongs to B. Uh, every subcover is also a refinement. So you may think that this is a space. It has this is a cover. If you will make it more small uh, or very small cover, this will be a refinement. But uh, its converse is not true. converse is not true in general. Sometimes refinement and cover may coincides. Okay. Uh, Refinement relations is very interesting. It is a lattice theory, but I will not enter in these things because this is not the topics. But I just for the informations, I will tell you refinement. Refinement. Okay, I will not go into more technical case. Refinement relations. Relations is transitive. This is true. Not reflexive. This is irreflexive. This is used in lattice theory. Asymmetry. Not symmetric. Okay. These preconditions informations will help us to discussions in our compact space and characterizations. That's all. Yes, we come to this position. Our discussions was that yes. So our definitions of compact space was that a space is topological space is a compact if it has a finite subcover. We mainly defined that is that open cover. The family of sets, open sets in X are said to be an open cover, and it is expected like this: X is equal to U of U. This is open sets, and this is a topological space, but initially it is a sets. It is sets. I am telling because this may be arbitrary sets. And the subcollections will be subcover if again a cover. Actually nothing else. Subcover is subcover, meaning is sub plus cover. Again a cover. That's all. Nothing else. A topological space will be compact. Compact if and only it is compact with the relative topology. Okay. A subset A of a topological space tau is compact if and only if it is compact with the relative topology. Is compact. This is implies that the compactness of the set A, it is defined on the compactness about the set A. Uh, as we know that every cover of A by open sets of A has a finite subcover. In other words, we must use the open sets in the subspace topology. Okay, generally a great inconvenience. Uh, we get a lucky break in the following result, which allow us to the open set in the original space A instead of the open set in the subspace A. So we introduce such definitions. A subset a, a subset A of a topological space tau is compact if and only if every cover of A by sets which are open in X has finite subcover. This is correct. We realize it by the definitions of real numbers. Yes, it has a cover AB. Suppose write down N. This is a open sets, no doubt. Okay, for N belongs to natural number, but it has no finite subcover. No finite subcover. So R or real number system usual topology is not compact. Yes, A discrete space is compact if and only if X is finite. Similarly, a co-countable topology is compact if and only if X is finite. We come to these examples, and next we will discuss more about it. Uh, it, it is the examples of uh, compact set and the conditions to be compact.